Okay, good morning, good afternoon, good day for you students that take the microprocessor lecture. So today is the, what is it, additional, additional, today we conduct additional lecture in order to understand about programming, yeah, programming 8085. I think you already familiar with the assembly language, but today lecture will be emphasis on the theory, background theory of each instruction set before we move further in the programming. Yeah. So I already asked the assistant to bring you the example of the programming because of the certain limitation. So the lecture will not cover all the examples of the program. The examples will be derived on the assistant class. Then we are right now dealing with the theory, theoretical background of the programming language. What I'm talking about is the programming language for the 8085. Okay, so as usual, this lecture will be used English as a primary language. So, and maybe in several occasions we will explain it in Bahasa. Okay, let's continue our discussion here. Okay, so this work is I get it from the New Horizon India.edu. It is from Kasturinagar. Yeah, you can check the link here for the further explanation. So I am recommended to read the programming 8085 from Intel. So this is the book because Intel is the manufacturer. So because of it is the manufacturer company, so it means that programming language explanation will more complete, yeah, than the the additional blocks. Okay, yeah, I just thought it that the book is the auxiliaries of our discussion. Okay, please make sure that you are focusing more on the practitioner, so then you can read or you can deliver the knowledge quite significant. Okay, so this is the instruction set of 8085. So the instruction set is actually the binary pattern designed inside the microprocessors to perform the specific function. Seperti yang sudah saya bilang kemarin bahwa uh, pola-pola yang didesain di dalam mikroprosesor itu mempunyai suatu fungsi yang spesifik dan itu ditulis itu berdasarkan pola tertentu. So the pattern is called the instruction set. Okay, so 8085 has a 246 instructions. So tiap-tiap instruksi itu direpresentasikan by the 8-bit binary value. Okay, 8 bit biner ya, direpresentasikan oleh 8 bit nilai biner. So this 8-bit binary value is being called as a opcode. Okay, opcode or instruction byte. So this is the classification of the instruction set. We have a data transfer function, arithmetic instruction, data transfer instruction, arithmetic instructions. We have a logical instructions, branching instruction atau percabangan, and control instructions. Okay. So we are gonna take a look first on the data transfer instruction. So this instruction move the data, of course, between registers or between memory and registers. So this instruction basically copy data from source to the destination. So it means that we are need an operand, okay, in order to satisfy the characteristic of satisfy the rules of data transfer instructions. While copying it, the content of source are not modified. Oke. Jadi intinya adalah mentransfer data dari sumber menuju ke tujuan. Jadi ketika melakukan transfer tidak ada modifikasi sumber, data sumber. Jadi apa adanya ditransportasikan menuju ke tujuan. Jadi proses data transfer ini membutuhkan operan untuk melakukannya. So the data transfer instruction, we have an opcode, operand, and description. So for an example, move opcode. So you have an operand which is RD, RS, RD, M, and memory and the RS register S. Okay. Jadi intinya adalah copy sumber ke tujuan. Jadi mempunyai destination registers. Jadi konten-konten sumber register itu tidak diubah. Tadi sudah saya bilang. Jadi apabila ada operan di dalam apabila operan itu adalah lokasi memori, maka lokasi memori itu mempunyai konten di dalamnya. Nah, maka kontennya itu akan dimasukkan ke dalam high and low registers gitu. Misalkan move B, C, move B, M, atau move M, C. Ini adalah contoh-contoh memberikan operand, ya, maksudnya mengirimkan data di mana operannya itu adalah konten dari suatu memori, alamat memori. Lalu kemudian data transfer instruction, oke, masih sama. Jadi MVI itu adalah move immediate 8 bit, ya. Jadi yang di move-kan, yang di transportasikan itu adalah data. Jadi the 8-bit data is stored in the destination register memory. Caranya gimana? MVIA, 57 hexa. So jadi ini sudah datanya, kemudian datanya akan ditransferkan menuju ke accumulator registers. Ini adalah move immediate. Jadi kalau bedanya MOV di sini, the difference between MOV di sini adalah here is the operand will be the memory location, and then the data is the content within the memory location. It is. Misalkan juga load register pair. Jadi ini ada 16 bit data yang akan ditransfer. Jadi besar sekali, ini bisa dimasukkan ke LXIH. LXIH. So this stands for the HL register high and low HNL registers. Oke. Misalkan BC itu kan bisa dijadikan satu. Jadi operan high registers and the low register, kalau Anda combine, it will become 16-bit because each of them is 8-bit. LDA, ya, load accumulator. Jadi LDA itu akan meload atau mentransformasikan data besarnya juga 16 bit. Gitu. Contohnya adalah LDA 2034. Oke. Load accumulator. Lalu LDAX, load accumulator indirect. Okay. The content of designated register pair point to a memory location. So this instruction copies the content of the memory location to the accumulator. So the content of either the register pair or the memory location are not altered. Of course, it is not being altered. For an example, LDAX-B. Gitu ya. Jadi ini akan melakukan loading ke akumulator tetapi secara indirect, di mana datanya itu ditunjuk pada memori, misalkan contohnya adalah B. Jadi dia menunjuk ke memori lokasi B, lalu kemudian otomatis isi dari memori lokasi B itu yang dikopikan ke akumulator. LHLD. So this instruction copies the content of memory location pointed out by 16-bit address to register L. It copies the content of next memory location of register H. Misalkan contohnya LHLD 2040 hexa. Jadi langsung saja, jadi dia akan mengcopy konten dari memori yang ditunjuk 2040 hexa ini. Gitu. Gitu ya. Lalu kemudian ini juga ada opcode-nya, namanya STA, Store Accumulator Directly. Oke. Jadi the contents of accumulator are copied into the memory location specified by the operand. Jadi konten dari akumulator itu di-copy ke dalam lokasi memori yang sudah dispesifikasi di operand. Seperti itu. Operannya nilainya adalah 16 bit. Gitu, ya. Lalu juga store accumulator tapi indirect. Nah, terus caranya gimana? Konten dari accumulator ini dikopikan ke memori lokasi yang spesifik. Jadi spesifiknya itu adanya di mana, yang ditunjuk oleh register pair. Misalkan B dan C register pair, seperti itu. Lalu ada SHLD. Jadi SHLD itu adalah melakukan store atau melakukan mentransportasikan memori ke dalam lokasi yang spesifik yang ditunjuk oleh 16 bit address, di mana kontennya itu awalnya dari mana? Dari register L gitu. Nah, terus kemudian konten register H tadi kan L ya. Nah, sekarang konten register H akan akan dikirimkan pada lokasi memori yang lain. Karena yang tadi itu L-nya itu sudah dikirimkan oleh register L ya. Jadi memori yang paling less significant tidak dikopikan, maksudnya sudah ditransferkan oleh register L, terus kemudian yang most significant bit akan dikopikan dari register H, seperti itu. Contohnya adalah SHLD 2550, seperti itu. XCHG ya, exchange HL with DE. Jadi ini akan simple saja, akan merubah swap ya. konten register H akan di-exchange dengan konten register D, konten register L akan di-exchange atau ditukar dengan konten register I. SHLD ini juga sama, konten register L akan disimpan ke dalam memori lokasi yang dispesifikasikan oleh alamat 16 bit. Konten register H akan disimpan ke dalam memori lokasi selanjutnya. Gitu. Contohnya adalah ini, SHLD 2550H. Ini juga sama, exchange HL with DE, ya sama. H di exchange, H is the exchange with the D, and L being exchanged with the E. So, after we already know how to store, how to transport the data, then we will move into the arithmetic instructions. So, this instruction will perform addition, subtraction, increment, and decrement. So remember that multiplication is actually the addition, but it is looping addition, right? And division is the looping of subtraction. Okay. Addition then. Any 8-bit numbers of content register or content of memory location can be added to the contents of accumulator. The result, the sum, is stored into the accumulator. No 2 or other 8-bit register can be added directly. For example, the content register P can be added directly to the content register E because it should use accumulator as the buffer. Subtraction. Any 8-bit numbers or the content register or content of memory location can be subtracted from the contents of accumulator. The result is stored into the accumulator as usual. Subtraction is performed by 2's complement form. If the result is negative, it is stored in the 2's complement form. No 2 other 8-bit register can be subtracted directly. So we have an increment and decrement. The 8-bit content of the register or memory location can be incremented or decremented by 1. Incremented means that the register will be, the bit will be added by 1, and decrement will be subtracted by 1. The 16-bit content of register pair can be incremented and decremented. We already knew that. So increment or decrement can be performed on any register or a memory location. So this is, for an example, the arithmetic instruction. We have add R register or memory to the accumulator. The content of register memory added content of accumulator, then the result will be stored in the accumulator again. If the operand is memory location, the address will be specified by HL pair register, or flags are modified to reflect the result of the addition, for example, at P or at memory. So the content of register memory, yeah, and carry flag, yeah, add with carry, add register or memory to accumulator with carry, and then the carry flag will be used in here. C, Y are added to the content of accumulator. So the result, of course, being stored into the accumulator. If the operand if in memory location, the address will be specified, of course, by HL pair. All flags are modified to reflect the result of the addition. For example, like at C, P, or at C, M. So we have at I, 8-bit data, at mediate to accumulator. It means that 8-bit data is added to the content of accumulator. The result, of course, it is being stored into the accumulator. All flags are modified to reflect the result of the addition. For example, at I45 hexa. We also have ACI, add immediate to accumulator with carry. So it means that 8-bit data and the carry flag are added to the contents of accumulator. The result will be stored in the accumulator. All flags are modified, of course, to reflect the result of the addition. For example, at immediate with carry ACI 45 hexa. From this example, you already know how to add, yeah, with carry or none with carry. So all the operation here, if you mention it carefully, we know that there is two kind of transfer or two kind of operation, which is immediate and immediately, or we sometimes call it straightforward. Yeah, straightforward operation, which is the data immediately stored to the registers, or maybe we can use what is it, the memory reference that being pointed by pointer. Okay, and then 16-bit contents of register pair are added to the contents of each all pair. We have TAD at register pair to each all pair. So the result is larger than 16-bit, then the carry flag is set if no other flag. No other flag are changed. So for example, TAD the B, which is what is B? B is the we call it as a register, 16-bit register, in order to add, yeah, add the 16-bit contents of register by another content, which is H and L pair. Okay, so this is the subtraction. It is same content register memory location subtracted from the subtracted of accumulator. The result will be stored in accumulator. So if the operand in memory location, it is already specified by H and L pair. So all flags are modified to reflect the result of subtraction. Same as PP, it is same, but subtract register or memory from accumulator with borrowing. So borrow is being saved by the flag. So then the flag is used for compute opcode SPP. It means that the content of register or memory location and borrow flag are subtracted from the contents of accumulator. The result, of course, being stored in the accumulator. So as UI subtract immediate data from accumulator. So the 8-bit data is subtracted from the contents of the accumulator. The result will be stored in the accumulator, and then all flags modified to reflect the result of the subtraction. So for example, subtract using the immediate from the accumulator as UI for 35 hexa. We also SPI subtract immediate data from accumulator with borrowing. The 8-bit data and the borrow flag is subtracted from the content of the accumulator. The result will be stored in the accumulator. For example, SPI 45 hexa. I and R, it means that increment register or memory by 1. The contents of register or memory location are incremented by 1. The result is stored in the same place. If the operand is the memory location, its address is specified by the concept of HL pair. So for example, INRB or INRM. So for example, I and X, yeah, the content of register pair are incremented by 1, the result is stored in the same place. For example, incremented X each. So we have a DCR, which is decrement or memory by 1. So the content of register being decremented -1. So the result will be stored in the same place. So if the operand is the memory location, the address will be specified by the contents of H and L pair. For example, TCRP or TCRM memory. So we have a TCX, decrement register pair by 1. So the content of register pair are decremented by 1. The result will be stored in the same place, which is TCX H, so that the result will be stored in the H. Yeah. So we also have the logical instruction. This instruction performed a logical instruction on the data stored in the registers, memory, and status flags. So we have a logical operation such as AND or XOR, rotate, compare, and complement. So AND or an XOR, any 8-bit data or the content of register or memory location can logically have an operation or operation and XOR operation with the contents of the accumulator. So the result will be stored in the accumulator. So rotate is also the same, but it is rotated. LSB goes to MSB, and then the other -1 LSB will be goes to the +1 MSB, and so on and so forth. So each bit in the accumulator can be shifted either left or right to the next position. So we also have a compare here. Compare meaning that you compare the data in order to achieve the comparison result. It is like if you can do the comparison, then you will create the logic because of the greater value or less value that being used as a point of reference. So the comparison will be for equality greater than and less than with the content of accumulator. The result is reflected in the status flags. Complement. Complement is the complement of the content of accumulator. So it means that 0 being replaced by 1 and vice versa. So for example, the logical instruction, you can use the CMP as a compare register, memory with accumulator. Yeah. So the result of the comparison will be setting in the flag of PSW. Okay. If A less than memory, the carrying flag is set. If A equal the memory, register memory, the 0 flag is set. If A greater than register memory, the carry 0 flag are reset. For example, CMP B or CMP M. We also have a compare immediate data with accumulator. So it means that it data is compared and contains with the contents of accumulator, the value being compared remain unchanged. The result will be alter the setting of flags such as PSW. This is the one. If A less than data, then the carry flag is reset, equal data 0 flag is set, and greater than, if A greater than the data, the carry and 0 flag are reset. For example, CPI 890. We have a logical AND register or memory with the accumulator. The content of accumulator are logically ANDed with the content of register or memory. The result will be placed in the accumulator, such as subtraction or addition. So as C and P it is the flags, are modified to reflect the result of the operation. CW is the reset, and AC is set. For an example, A and A, B or A and AM. We also have a logical instructions such as A and I, which is logical and immediate data with the accumulator. So the content of accumulator are logically ANDed with the 8-bit data. Same with the previous one, the result will be restored in the accumulator as C and P with are modified to reflect the result. So we have a XRA, which is exclusive OR. It is same with the N. So the result being placed in the accumulator as C and P will be modified to reflect the result of the operation because it is OR, yeah, exclusive or XOR. So C, Y and AC are reset. So we have a logical AND with immediate accumulator. So the content of accumulator are logically ANDed with the 8-bit data. The result will be placed in the accumulator. CY reset and AC is set. For example, ANI 86 hexa. We have a exclusive or memory with the accumulator XRA, yeah. So CY and AC are reset. So XRI P or XRI M, for example. So it is the same, the accumulator be placed in the accumulator. RA or logical with the memory accumulator. So it means that content of accumulator are logically or did with the content of register memory, right? So it is the same. So if the operand is the memory, location and address is specified by the content HL pair. So S, C, and P are modified to reflect the result. For example, we have a or I or immediate with accumulator. Content accumulator are logically or did by 8-bit data. Then the result will be placed in the accumulator. There are flags that being modified to reflect the result. For example, sign flag, zero flag, and parity flag, which is side CW and ACR being reset. We have a XRA because it is the operand. If operand is a memory location, the address will be specified by content H and a pair. Okay, so S, C, and P, the famous flags for the logical instruction, will be modified to reflect the result of the operation. So we have XRI, XOR immediate accumulator, CY and AC are both reset. So of course it is 8-bit data operation, and the result will be, of course, placed in the accumulator. We have a rotate accumulator left here, RLC. So the data will be formed as following. The T7 is being placed by position T0 as well as the carry flag. CY is modified according to T7 as PAC are not affected. Okay. So we have a rotate accumulator left. We have a rotate accumulator right. It is the same. It is to the right. So we have a rotate accumulator left through carry. It means that its bit of the accumulator is rotated left by one position through the carry flag. So bit 7 is placed in the carry flag, and the carry flag is placed at least significant with the position of D0. So rotate right with the carry, It is the same with the left. We have a complement accumulator. The contents of the accumulator are being complemented. No flags are affected. This is complement carry, so carry flag is also complemented. So we have ability to set carry, whether it is set carry or it means that no flags are affected. Yeah. So it means that you set the carry set to 1. So we have a branching instruction here. It means that operasi bercabang. Jadi Anda bisa gunakan logika-logika if atau logika-logika while di sini ya. So the instruction is alter the conditional or unconditional. For example, jump unconditionally ya. Anda bisa masuk ke dalam address supaya Anda bisa jump ke instruksi lebih lanjut. Contohnya adalah jump to 034 hexa. It means that you jump to this kind of specific location. Lalu kemudian masuk sini, jump 0, jump conditionally. The program sequence is transferred to the memory specified by 16-bit address given to the operand based on specific flag on the PSW. Oke, GX misalkan GC ya. Jadi jam 0 GC. Jadi Anda bisa masukkan di situ. Jadi contohnya jam conditionally ada jam 0, jam non 0, jam positif, jam minus, jam 0. I mean this is jam carry, this is jam 0, so this is non 0. Jam if parity even, jam parity odd. Yeah, this is the status flag. Branching instruction, we call it as call unconditionally. The program sequence transferred to the memory. Location specified by 16-bit address given by operand. Before the transfer, the data address next instruction. After call, the contents of the program counter is pushed into the stack. Jadi ini juga sama CX call conditionally. So it means that the program sequence is transferred to the memory location, 16-bit address given in the operand based on specified flag on the PSW. Before the transfer the address of the next instruction after call, the contents of the program counter is pushed into the stack. Contohnya adalah jam conditional, bukan jam tapi call ya. Call if carry, call on carry dan lain sebagainya. Ini adalah masih branch instruction. If you call, then you should return. Jadi dia bisa masuk ke program instruksi yang lain, tapi juga jangan lupa return. So ketika masuk ke tadi sudah call ya, sudah jam, lalu kemudian masuk ke return. The program sequence is transferred from the subroutine to the calling program. The return means that you go back to the previous condition ya. Jadi kembali ke kondisi ketika Anda lakukan jam tadi. Itu adalah return. So ini adalah jam conditionally. Contohnya adalah jam not jump but return conditionally. Contohnya adalah return carry, return on carry dan lain sebagainya. Kita punya restart, software interrupts ya. Jadi misalkan kita mau mereset karena ada suatu trouble, juga bisa diberlakukan di 8085. So the reset instruction jump the control to one of 8 memory location depending upon the number. So there are used as a software instruction in a program to transfer program execution to one of 8 location. Misalkan contohnya adalah ini. Jadi akan masuk ke dalam salah satu dari 8 lokasi alamat ya. Misalkan adalah jump instruction, ASD instruction jump on the control of 1/8 memory location depending on the number. So there are used software instruction in program to transfer execution to one of 8 location, for example like this. Akan masuk ke sini ya. Kita punya control instruction. It is to control the instruction of the operation of microprocessor. Contohnya adalah ini. Jadi ini adalah control instruction, opcode-nya adalah NOP, no operation is performed, the instruction is fetched and decoded, but no operation is executed. For example, NOP, operannya nggak ada, operation, it means that you already finish your line. Halt also doing the same, yeah, it is necessary to exit the program. So interrupt or reset is necessary being formed, needed in order to exit with this state, within this state. Ini adalah disable interrupt jika Anda mau mendisable interrupt ya. Enable interrupt ini juga sama. RIM, read interrupt mask, ini adalah multipurpose instruction used to read the status interrupt 7.5, 6.5, and 5.5 and read the serial data from the input bit. This is the RIM, yeah, read interrupt mask. The instruction load 8-bit accumulator with the following interpretation. This is the RIM instruction. Serial input bit will be placed into most significant bit, and the last significant bit D0, D1, and D2 is the interrupt mask. Yeah, you can do the put into high signal if you desire to enable one of those interrupt mask. Interrupt enable, this is the flip-flop used if bit is 1. This one is interrupt pending if bit is 1. Okay, so this is the control instruction. SIM, set interrupt mask. So this is the multipurpose, of course, and used to implement the 8085 interrupt 7.5, 6.5, and 5.5 and serial data output. Yeah. This is the read interrupt mask, and this is the set interrupt mask. So this is the output data, and this is the serial data enable. The use is the aim is for the set interrupt mask. If RIM is for the read interrupt, this is for the set. You can do your own interrupt, yeah, because it is actively being controlled by you. Okay, same D0, D1, D2 is the proprietary of the interrupt mask. M7.5, 6.5, and so on and so forth. Thank you. May God bless you always.